Hello, my name's Ed Bunker and I'm an exploration geologist within the Minerals and Mining team at CGG. Today, I'd like to talk you through our integrated perspective of the lithium mineral system by showing you a few examples of exploration tools that we've developed for our clients. Before I get into all of that, I wanted to talk about why lithium is so important in this modern landscape. So the physical and chemical properties of lithium, namely its high charge density and its low ionic mass, make it the best element that we could possibly have for making high charge density batteries. And these are really crucial in those applications where you want mobility of the battery, such as within an electric car or a mobile phone, because this makes the electronics as light as they possibly could be. The demand of lithium is projected to increase by about 8 times over the next decade for this exact reason. Um, and this is all primarily driven by the energy transition and the need for batteries for storage of electricity. Likewise, the supply of lithium is also strategically vulnerable because the majority of lithium is only produced in a few countries, namely Australia, Chile, Argentina, and to a lesser degree China. But also, more importantly, the majority of lithium is processed within China. And so this kind of drives home how strategically important it is to have a domestic supply of lithium. In order to explore for lithium, you need to understand how lithium moves within and at the surface of the Earth. So lithium's distribution within the Earth's crust is primarily derived by its desire to be in as free a state as possible. Lithium likes to be within fluids over rocks and likes to be within gases over fluids. So through the process of magmatic differentiation, you can imagine that lithium would be naturally concentrated within the residual magma. But this is a problem in geological examples like you see on the left, where we have a lithium pegmatite, because here the magma has differentiated to the point where it can't differentiate anymore. It's very hydrous, very enriched magma, very refractory magma. So lithium is enriched within that magma, but at that point there's no choice but for it to be partitioned into the lattice of a crystal. So we have these pegmatites which are enriched with lithium-bearing minerals such as spodumene and petalite. Interestingly, in favorable geological conditions, maybe with fractures, waters can interact with these minerals and liberate the lithium from those minerals. But that's a side point to today. So in examples where we have a fractionated magma or a felsic magma, lithium can be transported up into the conduit and erupted at the surface. So in felsic environments like the Western Andean margin of today, eruptions occur, very large eruptions, and lithium is lost through devolatilization of that magma to the atmosphere. However, some of that lithium is trapped behind in the residual magmas. So we have eruption of rhyolitic magmas, and it forms magmatic deposits such as ignimbrites on the surface today. What's interesting about ignimbrites is that they have a glassy matrix. So oftentimes, rather than lithium being trapped within the lattice of a crystal, it's actually trapped within a glass. And also, these ignimbrites also have a high surface area due to the vesicularity of that glass. Now, these are two interesting components because a glass means that the lithium is not trapped within a lattice, and because it has a high surface area, that means that there's a lot of surface area for reactions to occur. And some research that was carried out and published only this year showed that lithium often can easily be remobilized from these rhyolites, providing that they are still cooling. So that's a really important implication there, that lithium can be remobilized from these magmas at or near the time of deposition of those rhyolites and those ignimbrites. Now, interestingly, as I've said, lithium can be remobilized through interaction with water. So the waters would be driven off of these rhyolites with an enriched lithium content. Now, the lithium in these rhyolites is only at maybe 50 to 100 ppm, which is very low. Well, it's certainly not all grade, let's just say that. Um, and likewise, you'd expect that the waters would not have a significantly enriched lithium content. But what's crucial here is that the content of lithium relative to other cations within the fluids, so the lithium to cation ratio is increased. So calcium and other cations won't be derived from these magmas, but lithium would be, and that can be transported downstream. Another important contributor of lithium into this kind of surface water system is geothermal springs that are derived from active magmatic systems. So you can see on this figure we have a finger of magma that's intruded into the into the shallow crust, and as it cools, it begins to condense fluids from that magma, and these fluids are enriched with lithium and other elements. And sometimes these fluids extrude at the surface, and in the geothermal brine screening product that I'll speak about later, we can see this happening in the modern day in the Atacama and other regions. And these fluids tend to have lithium enrichment of maybe 50 ppm, maybe slightly higher than that. And that's a really significant enrichment relative to the lithium being derived from these ignimbrites. So it's a massive step up in lithium enrichment. And this is seen as a key contributor to environments such as the Atacama and the Salada Uyuni. So these lithium enriched brines, or these lithium bearing brines, are transported down into what we might consider an endorheic basin. This means that fluids can flow into the basin, but there's no way for the fluids to flow out of the basin. And as this fluid sits here, it begins to evaporate. And providing that the evaporation rate outstrips the precipitation rate, the volume of this water will begin to diminish. So that's a crucial implication that we know of today, is that these environments are arid or hyper-arid are best for the enrichment of lithium. So the volume of the water diminishes, lithium is enriched within the residual brine, but so are other cations such as sodium and potassium. But as they reach high concentration, sodium and potassium begin to be stripped out through the precipitation of evaporitic minerals such as halite and gypsum. So halite and gypsum and other evaporite minerals will be precipitated out, but lithium wants to stay in the solution for as long as it possibly can. So what we actually see is that we have a residual brine that's lithium enriched and doesn't seem to ever really want to precipitate lithium if it doesn't have to. Now, the interesting paradigm that I'm going to speak about later is that the lithium in these brines has a long residence time. It can actually sit there for geologically long periods of time. And so over that geological time, it may be buried, maybe by the eruption of another ignimbrite, or maybe through the deposition of a gravel. And providing that we have a good aquifer sitting here, the lithium can sit and just live within that basin for as long as it needs to. So that's what we call a paleosalar. So a salar that's now buried, no longer active, no longer being enriched, but sitting there with a lithium enriched brine in the pore space. And then just to finish the story, we also have observations from oil fields where we see these lithium enriched brines. And it's still quite highly debated what's the origin of these lithium enriched brines. Perhaps it's specific to the basin, or perhaps not. Perhaps it has a relationship to the preceding paleosalars that we were just talking about. And we also have these things called basinal brines, where it's not very clear what the geological context of the brine is. From where was it derived? From where was the lithium derived? It's not very clear in general. So that's what we call a basinal brine, and that completes the story of the lithium mineral system as we see it. What's exciting really though is that over 64% of the lithium reserves that we know of today sit within these brines. So we're not really looking at, well, hard rock is still an important source of lithium, but as technology advances, as these new methods of lithium extraction kind of progress, we're seeing an increased proportion of lithium reserves sitting within these brines. This estimate was actually conducted in 2017, so it's most likely an underestimate in today's climate. So now I want to talk to you about a few tools that CGG have developed for the exploration of lithium-enriched brines. The first of which being a screening tool for geothermal brines to understand the distribution of lithium and other associated elements. So this is driven by the principle that through the extraction of geothermal fluids, we're actually extracting a fluid which is bearing interesting chemistry, and is there a potential for extraction of elements from that interesting brine as we're producing heat from it. So co-production of energy and minerals. We know that lithium is an interesting mineral because we're aware of technologies that I'm going to speak about later which facilitate extraction of lithium from these brines, but we also know that there are other elements within these brines of value, perhaps silicon, perhaps zinc, perhaps other elements. And so it's important to understand the full periodic table of these fluids. We also know that some elements like boron, fluorine, hydrogen sulfide, they are deleterious, dangerous elements that we really don't want to have in the fluids, because if we want to extract these favorable elements, it's better to not have any boron or fluorine. But really it comes down to how effective your processes and safe your processes are into how sensitive you are to those elements. So talking about these kind of deleterious elements in a bit more detail, we know of a few, or actually quite a wide range of methods to extract lithium from brines, and new ones seem to come around every day. So there are a range of technologies that are facilitating extraction of lithium from these brines. So sorption technologies such as ion exchange, resins, metal oxide sorbents, and solvent separations. These are all interesting methods with different exotic materials that strip the lithium out of these brines. We also have semi-permeable membranes that facilitate the transportation of lithium ions and leave behind the residual fluid and components behind. We also have electrochemical methods of concentration of the lithium. So we have a range of different ways to get lithium out of these fluids, but they all have unique challenges and unique opportunities. So some of these methods are very sensitive to temperature or pH of the fluid. So understanding the temperature and pH is really crucial if you have a particular method of extraction in mind. Likewise, some of these methods are optimized and can work really well with difficult elements like potassium, and potassium likes to, or sorry, magnesium. Magnesium likes to move like lithium within these systems, but other methods of extraction will really struggle to separate lithium from magnesium. So understanding what method is best for the particular fluid you have is really crucial. But we've taken an approach of understanding our base understanding of the lithium mineral system in developing these data sets. So we want to understand the source rocks, we want to understand the where this lithium ends up, how it gets there, how the concentration occurs. And so we've built a data set that helps in understanding that. So to summarize what this data set looks like, we have a range of different a range of different data layers, including the hard rock geology. So this gives an indication of what the lithium enrichment in the hard rock was, because as I've discussed already, lithium can be liberated from certain hard rocks and moved into fluids, and this is crucial in that lithium enrichment journey. We've also included other key layers, such as the location and production vectors of particular geothermal plants, and this is an enriched data set relative to what's available in the public domain. We've gone through and QC'd this data set, accurately cited the data points, which is really a key stage. And then we've also included key vectors, key data parts like the flow rates, which are really important if you want to understand areas which have high potential for the generation of geothermal energy. So alongside the chemistry of these fluids, as well as the physical properties such as pH, TDS, and temperature, we've developed these accessory data layers. Now, what's exciting about this data set is that a range of different clients can approach this data set and interrogate it with different things in mind. So they might have different direct lithium extraction technologies, or as a company, they might have different priorities. So for instance, maybe they only care about the lithium and they don't care about the geothermal energy. So they won't care if the water is hot, cold, lukewarm, whatever. Conversely, some companies really want to generate heat and offset that heat with the production of minerals, so using the energy they produce to produce minerals using some technologies. So a range of different companies can approach this data set, which is a multi-client data set, and generate different answers to where the ideal brine is and help them in their mineral exploration. I want to switch gears now and talk about lithium target generation in the high Andes using satellite-derived techniques. So why did we pick the high Andes for this study? Well, I mean the most obvious reason is that over 54% of global lithium resources sit within this region titled the Lithium Triangle. But what we also know is this region is more broad than only the Lithium Triangle, which is defined by three kind of major lithium brine deposits. So using our satellite-derived techniques, we've been able to cover a wider swathe of this area than just the lithium triangle in our search for lithium enriched brines. Um, so this area is optimized because of the climate conditions. There's no cloud cover. It's also very low vegetation cover, so it's ideal for looking at using satellite-derived techniques. The salars that we're looking at are also near surface basins that are easily characterized from space or on the ground. I've already given you an overview of the lithium mineral system, but to focus in on these brines, so we have that lithium enriched source rocks such as the rhyolitic ignimbrites. Lithium can be derived from those rocks and transported down into endorheic basins where they accumulate. And through evaporation, the brines in those basins are subsequently enriched. We also have the contribution of lithium from other sources, such as those hot springs that we talked about earlier. And the interesting exploration opportunity here is, can we find lithium-enriched brines that are sitting within buried basins? So I'm talking about shallowly buried basins that we can characterize using satellite-derived techniques. Now, how do we do that? Well, firstly, we need to bring together disparate data sets. So one of the key data sets we've been using are geological maps to understand the geology of these systems. But we have a really big challenge when we're working on large-scale exploration projects like this one, that our geological search space covers several different countries. So we have northern Chile, southwestern Bolivia, and northwestern Argentina all sitting within this search space. All of the geological maps in this region are produced at different scales, they use different symbology, and they also have different names for geological units. And this is a huge challenge when you're searching in this region. So what CGG have done is we've merged and created a unified geological map over this study area, and that's produced at 1 to 500K. And what this means is that when you search across the borders between Chile and Bolivia, the rocks can have equivalent names and the same name. The units and boundaries all match up, and this is all produced in a unified map. So we've shown this to clients, and they've expressed that this in itself is a valuable output that they'd like to buy as a standalone product. But alongside this, we've generated a range of valuable satellite-derived derivatives and data sets. So to start on the left, we have a visual light spectrum bare Earth model produced through the Sentinel-2 satellite. We also have a multispectral bare Earth model derived from ASTER data, which is shown in the second from the left figure. Using digital elevation models, we've also been able to create derivatives through our in-house processing techniques that are valuable to this project. So in the middle figure, we have a figure that shows the areas that we've derived as river catchments and also the flow paths. And obviously in this hyper-arid region where waters rarely flow, it's difficult to predict where these waters would actually flow if the rain were to fall. But using our DM techniques, we've actually been able to derive those paths. We've also brought together key geological data sets. So in red on the second from the right figure, we have ignimbrites from recent times, and this is what we regard as our lithium-enriched source rock. We also have in blue the distribution at the surface of modern-day salars, and this is an important variable to understand. The final piece of the puzzle is the digital elevation model shown on the right-hand figure, which is a flat area derivative which we've created through in-house processing. And this shows flat areas which are shown in stippled regions of blue, red and yellow. And this is important for predicting where waters would accumulate were water to flow. Now I'm going to show how we use this in action. So we're in a region of northwestern Argentina here. We can map the flow path, the drainage catchments here in red, and we can map the distribution of the ignimbrites here in orange. This is a crucial data set because it actually shows the fertility of this basin. If there weren't any lithium-enriched ignimbrites, there would be no chance for lithium enrichment in the basin. We can map the flow paths running, and what we can see is that these flow paths run through the ignimbrites and into the center of this basin. And we can predict where the waters would accumulate, which is shown in light blue here. We can validate this approach and how it can generate novel, interesting lithium-enriched targets because junior companies are already exploring in this region. So we have NRG Metals to the north and we have Lake Resources to the south. And to give you an idea of the size of the prize in this region, the Lake Resources concession in the south, you can see a green polygon on that figure to the right-hand side. And that's a JORC compliant resource of 4 million tonnes of lithium carbonate equivalent. This company is also within the same concession looking to expand this by 10 million tonnes through further exploration. So this gives you an idea of how big these concessions can possibly be. I'm going to close off now by just sharing a few comments on oilfield brines and where we as CGG are going. So obviously CGG has a background in oil and gas research, understanding these basins in detail. It's also known that some of these basins, but not all of them, contain brines that are lithium enriched. So understanding the controls on why some basins have these lithium enriched brines and why others do not is a really interesting research question that we are looking at within CGG. Now, understanding like these lithium enriched brines have a long residence time, so we know that over geological time they are preserved, and that's really crucial in understanding where they could be in the modern day. And the sources of this lithium are not very well understood. So researching what are the possible sources is a crucial question that we're trying to answer. And as we know, these lithium enriched brines sitting within oil fields are becoming increasingly economic and interesting due to the range of lithium extraction technologies that are emerging onto the market today. Now, I want to use a short case study of the Smackover Formation in the Gulf of Mexico, which is a rather well-known lithium enriched interval. So the Smackover Formation sits here in the lower regions of the Gulf of Mexico basin, and it has very enriched lithium values exceeding 1000 milligrams per litre in locally concentrated areas, but in general, the lithium values are within the hundreds of milligrams of litres, which is highly economic at today's kind of prices, so very interesting for further research and development. Interestingly, the waters sitting above the Smackover Formation, we do have brines sitting within these geological intervals, but generally the lithium enrichment is very low, so generally less than 60 milligrams per litre. So there's a big question there about why is the Smackover Formation so lithium enriched relative to the other rocks in this basin. Now, what we know about this basin is the Smackover Formation is a very good aquifer. It's about 300 meters of thick of limestone, and we have this lithium enriched brine. Above it, we have rather good cap rocks, the Haynesville and Bossier shales. These are low permeability shale units, and they immediately overlie the Smackover. And beneath the Smackover, we have the Luan salt, which is generally appreciated to be the lithium source rock. Now, if you think back to my paleosolar examples from earlier, we know that lithium can be enriched through evaporation, and likewise, the Luan salt will have formed in a hyperarid environment through progressive evaporation of waters. So it's not hard to think that maybe evaporation led to the enrichment of lithium-enriched brines that sit within the Luan salt. Now, there are still plenty of open questions here. What is the lithium source? Now, I've argued that a paleobrine sitting within the Luan salt could have been liberated and moved up into the Smackover Formation. Other people believe that perhaps the lithium was derived from dissolution of the Luan salt. Perhaps the lithium was captured within salt crystals within the Luan. Others believe that it could have been due to alteration of silicates. So really those two questions could be answered by looking at, is there evidence for dissolution of the Luan salts, and also is there evidence for any alteration of silicates? But from our perspective, the most parsimonious answer, it could be that paleobrines were sitting within the Luan salt that had been there since the formation of the Luan salt, and then through maybe a tectonic event were liberated into the overlying Smackover Formation. Other key variables here is aquifer quality. So the Smackover is a great aquifer. We know that it hosted oil before it hosted the lithium enriched brines. So the lithium in brine was kept within a small volume, a relatively small volume relative to the full basin, and it was trapped there by a high quality cap rock, so the Haynesville and the Bossier shales, and that was crucial to the concentration of this economic lithium brine. So I'm just going to leave it at that. I thank you very much for your attention, and I hope you enjoy the rest of your conference.